So whenever I'm home, I get to help guys. Welcome to week 12, I'm told. Gosh, we are closing in on 80% done anyway. Getting pretty far along here. Couple of announcements for you as we get started on another new week. First of all, there is a homework assignment that is due tonight. I did not have much office hour business the last 2 or 3 sessions from either of my classes, so I'm assuming you're all waiting until this evening to ask your questions. I'll be around right after my second class. I'll spend an hour down there, and also in Zoom if you'd rather stop by Zoom. And then I will take a break, and then I'll come back and have another hour. I probably won't get out of the office tonight till about midnight, which is kind of normal on a Monday or Wednesday night. So feel free to jump in with me on Zoom if you've got any questions. The next homework, I ordinarily would probably make it due on Friday because we have an exam next week on Wednesday, and I don't like homework to be drifting into the exam studying time that much. However, I am going to be out of town, so I've decided to make the next homework assignment due next Monday. It's only 2 days before the midterm, though. I would recommend that you try to get the assignment done by Friday as best as you can. I am leaving town Wednesday evening on have any of you ever taken a red-eye flight before?
Yeah.
You get on the plane like and fly during the night. Because I'm flying east. I'm going kind of 2/3 of the way across the country. So I will be flying overnight Wednesday night. I'll probably be here for my office hours until about 9 o'clock. Then I got to go to the airport. I'm taking this trip. I'll be gone Thursday, Friday, Saturday, and Sunday. I'm flying back Monday morning to LAX at 7 a.m. Can I get here by 10 a.m.?
LAX?
Yeah. If I land at 7 a.m. and I have class here at 10 a.m., am I going to make it? It's the only thing I could do.
Traffic sound.
What day of the week?
3 hours. It takes 3 hours to get from LAX to Fullerton?
No, you should.
No, it's about an hour, 30 minutes.
Okay, so I ought to be all right.
You might be fine.
Unless the plane is like late.
You have a bag.
No, I'm not checking a bag. I'm running off the plane, running straight to my car. I'm actually gonna drive out there and just have my car, so.
You'll be fine.
Yeah, that'll be absolutely fine.
Okay, good. Okay,
Yeah.
I don't know what I'm gonna do. If I'm racing to class, I'm gonna come in all disheveled if I have to. I don't want to miss class on Monday. So anyway, I am gonna be gone Thursday, Friday, Saturday, and Sunday. My plan is to have office hours in Zoom on Friday. My normal office hours on Friday, so that it'll be Zoom only. Sunday, I'm not exactly sure because my Sunday hours are really pretty late, even West Coast time, and I'm going to be 2 hours east of here. So I may not do a Sunday night office hour, which is why I'm just going to make the next homework due on Monday. So in case you do have some questions, hopefully not a massive number of things left over for next week on Monday, but I will let you turn in that next homework on Monday, and it will be possible to talk to me in person next week on Monday. I might be half awake, but I'll be here. So that should work. Yesterday I did a review session. There are 21 problems on this review session number 2 handout. I only did 7 out of the 21 problems. I got kind of carried away, I guess you could say. I got some of them done, but there's a lot that I didn't get done. I'm going to do another review, which will be in class next week on Monday. So we'll just be reviewing in class. We'll have 2 more hours to crank through more of these, but I'm also going to put some more of these into my lecture as some of the examples we're going to do as well. So I think we'll get through most of this. If I don't end up solving every problem in the review session handout, of course, I've got them all typed up. So you can read the solutions as well to anything I don't do. I'll try to make sure I've covered all the really big important ones that I think are really good to look at. But anyway, so we did the review session. I sent out a link to it. It's about a 2.5 hour video of what we did yesterday for those of you who were able to make it. If you weren't, no worries. Just watch the video if you're interested at some point. That's probably a good thing to look at. That midterm 2 resources folder also has a sample exam. It also has just a review packet with kind of an overview of what are the sections that are going to be covered, what are the buzzwords you need to know, what kind of things should you be able to do, what kind of questions, right, that you should be able to answer, stuff like that, along with another sort of batch of practice problems in that packet. So between the review packet, the review session, and the sample test, there's quite a bit of problems for you to take a look at. whenever you have some time to do that. So the exam is next week on Wednesday. So I will be fully back next week, Monday. I have some extra office hours next week on Tuesday. I'll be trying to stay pretty close to the office in case people are trying to get things figured out and ready to go. But yeah, look at the sample test for an idea of kind of what to expect in terms of the types of questions, the length of the exam, that kind of stuff. You've already taken one exam with me, so you have at least a little bit of an idea kind of what type of things I like to do. But anybody have any questions about any of that, the schedule here? So I've gotten a couple of rough drafts of papers, or at least partial rough drafts of partial papers. That's been great. You can send those to me anytime you want. At some point over the next week, you're going to need to probably set that down to focus on the midterm that's coming up. That's really more important probably in the short term. And then there'll be time to continue to work on those papers after the midterm. I forget what date I put for the due date. It's sometime in early May. So there'll be a little bit more time to go, at least an extra week and a half, I think, after the exam. So yeah, that's kind of where we are at. There will only be, after today's homework, there's only going to be two or three more homeworks left. So there's not that many more homeworks to go. But there is one for next Monday as well. All right, let's kind of review. I kind of unfortunately went a little slow last Wednesday. I got hung up on that one thing I had gone off script for, so that slowed me down. I want to catch up a little ground here, and there's two really big theorems we're going to do today. Okay, this is not one of them. This is some recap of one that we did last Wednesday. So let's just get the framework again. We have two fields, F and K. U is just any element out of K for starters, and we can build a sort of intermediate field, which is written as the simple extension F of U. This is just the smallest field that contains U and F. And of course, there's trivial results that could occur. It could be that F of U is just F, or it could be that F of U is equal to K. Either of those is possible. But alternatively, it could be that there is a legitimately interesting field sandwiched strictly between F and K. So anything is possible here, but by its very definition, it is a field. Okay, it is a field one way or the other. The smallest field, in fact, that contains all of F and this one additional element U that we have adjoined. Obviously, if you're going to adjoin U to F, then in order to make this thing closed under addition and subtraction and multiplication and division, you're going to have to close it up under powers and under reciprocals and in all kinds of addition and subtraction expressions involving U, right? All of those things will have to be in this simple extension F of U. Okay. So then we had this theorem and we wrote this down and we actually proved this. This is the one where I sort of did the proof before I stated it last week. Let's just write it down again here. Again, F is contained in K as fields. And now I'm going to assume actually that U is algebraic over F. This just means that there is some polynomial with coefficients in F that is satisfied by U. So that is a pretty powerful concept. If U satisfies a polynomial, as soon as U satisfies a polynomial with coefficients in F, then what you can do is you can look at all possible polynomials in F of X that have U as a root and find the best one, right? And the best one is this IRR of U comma F, right? So the theorem says that this exists. There exists a unique, monic, irreducible polynomial with coefficients in capital F that has U as a root. Okay, so you can make it monic. That just means the leading coefficient is a 1. The polynomial is irreducible, right? If it wasn't irreducible, then you could factor it and U would be a root of one of those factors, which would have lower degree, right? So somehow U has, or sorry, the irreducible polynomial of U over F has the smallest possible degree of any polynomial that is satisfied by U. In other words, that has U as a root. So there actually is a little, I have a couple of remarks here. These things I don't think I said last time. So I'll just write them down here. This IRR of U comma F, the you can call it the irreducible polynomial of u over f if you want, but it is also sometimes called something else. It is sometimes called, and the book uses this terminology. It is called the minimal polynomial, And we can say the minimal polynomial. There will only be one, because this is a unique polynomial. The minimal polynomial of u over f. So that's just another way of referring to this polynomial in theorem 11.6. It's the minimal polynomial. And then another piece of terminology here, and I think this did come up briefly in the group work that we did last Wednesday, but I didn't officially put it into the definitions. So I'm going to define it right here as a remark. The degree of an element u, right? So if I want to know the degree of some u over the field f, this is just by definition, the degree of the polynomial IRR of u comma f. It's the degree of that minimal polynomial of u over f. So whatever that degree is, it's just a number. It's just a number, and that's the definition of that. And then finally, one last remark, which is actually more or less encompassed already in the statement of the theorem, but I would just like to write it down anyway, which is that if we find some polynomial g that has u as a root, right? If g of u is equal to 0, then this minimal polynomial IRR of u comma f, right, must divide g of x. So that's basically so we have a unique monic irreducible polynomial that is satisfied by u. All other polynomials that are satisfied by u have to be multiples of that polynomial. So pretty straightforward. We wrote this down last time as well. So just a couple of definitions and remarks here to remind you about. Does this all make sense to everyone? Right? So there's kind of a best polynomial that we are associating with each element u, which is algebraic over f. Yes.
In the stuff we did on Wednesday, we talked about a maximal ideal generated by the irreducible polynomial.
Yes.
The minimal polynomial.
Yes.
Is there a name for that too?
Not particularly. No, not particularly, but we are going to be making good reference to that in one of the two big theorems that I'm going to be presenting today. So that is an ideal that we want to have in mind. Remember that, guys? Did you all watch my video yet on the neon markers on the blackboard? Right. One of the results was basically that these principal ideals generated by P of X are maximal ideals if and only if the polynomial is irreducible over the field. So yeah, that's another good point. It's not listed here, but definitely worthwhile. So let's just do a couple of quick warm-ups just to kind of get rolling. I lost a little steam on Wednesday by getting screwed up on that one example. So let me try to point out that it's not usually that bad with a couple of warm-up problems here. So what is, let's just try to calculate the irreducible polynomials of some relatively easy things. So let's take the complex number I and find the best polynomial that has I as a root over the real numbers. Does anybody have a conjecture what that would be? X squared plus 1. Exactly. Obviously, if we plug I into that, we do get 0. So I is a root of this polynomial, and this is the lowest degree polynomial that would have I as a root, assuming we're allowing only real coefficients. I mean, this thing does factor, of course, but it does not factor over R, it factors over the complex numbers. So in fact, if I wanted to know the irreducible polynomial of I over C, right, what would that be?
X minus I.
Exactly. Now I'm allowed to use I as a coefficient in the polynomial, and that cuts the degree of this irreducible polynomial down even lower here. So those are pretty easy. Anything of degree 1 is obviously irreducible. Anything of degree 2 is irreducible as long as there's no roots, and there are no roots of this polynomial in R, so it is irreducible over R. pretty easy examples here. It's not always quite so obvious, of course, so we could do something a little more interesting. Suppose I had the square root of 3 times I plus the square root of 2, and I wanted to do the irreducible polynomial of that element over Q this time. So we've practiced a few of these already, but let's just do this one. This one is much easier than the one that I tried to do the other day. So we can just call this U. Okay, and we have a number of things about this element U that are not rational. So we need to kind of get rid of those things. And one way to do it is to square both sides. So this is what U is, then U squared would be, well, square root of 3 times I. When I square that, I get -3. And when I square radical 2, I get 2. And then I would have a cross term, which would be 2 radical 6 times I, like that. And so I can move everything but the 2 radical 6 I term to the left side. So it will become U squared plus 1 equals 2 radical 6 times I. And now I can square both sides again. And on the left, when I do that, I'll get, so I'll just square both sides, right? So on the left, when I do that, I'll get U to the 4th plus 2U squared plus 1. And on the right-hand side, I will get -24, I believe. And so now I can add 24 to the left side, and I'll have U to the 4th plus 2U squared plus 25. That much is equal to 0. And you can see immediately that this polynomial, in fact, this is going to be the answer. This is going to be the answer here, x to the 4th plus 2x squared plus 25. You can see clearly that it has no roots in Q. That's because every term is positive, right? So you can't get 0 to come out of something like that. Even if you weren't sure about that, you could use the rational roots test and very quickly plug in plus and minus 1, plus and minus 5, and plus and minus 25. Nothing will serve as a root. So the rational roots test produces no roots there. And then, of course, the other possibility is that this could be factorable over Q as a product of 2 irreducible quadratics. So you could imagine, and we did this last time, we tried to, set up some equations, something like this. We're getting pretty good practice at this. I did one of these yesterday as well in the review session. So if you match up the coefficients, right? This just becomes x to the 4th plus a plus c x cubed plus b plus d plus ac x squared, and then plus ad plus bc x, and then plus bd, right? And we can create a series of equations out of that then. So it takes a little bit of time to do this. The x cubed coefficient had better be 0, right? The x squared coefficient had better be 2. And the x coefficient, which is AD plus BC, had better be 0. And then B times D had better be 25. So we're trying to prove that this is impossible. And when I say impossible, I mean impossible with rational values of A, B, C, and D. So just to be totally clear about that, right? A, B, C, and D should be rational because we're looking for the irreducible polynomial over Q. Exactly. Okay, well, we've seen kind of how this works before. We can replace C with -A, and then in the third equation, if we replace C with -A and factor out an A, we actually would get the product of A and the quantity D minus B. And at this point, we have two cases. Either A is 0 or B is equal to D, right? These are the only two possibilities. And we can just analyze each of them kind of one by one. In the case when, let's see, when A is equal to 0, then what do we know? We know that B plus D then would equal 2, right? In this equation, B plus D would be 2. If A is 0, then B plus D is 2, but B times D is 25. Right, so it's this just depends how you want to play the game here. I would probably just substitute D with two minus B into the second equation. This is nonlinear mathematics, guys. We can't just use a bunch of stuff from linear algebra right now. These are not quite that nice of equations. When you rearrange this expression, you'll end up getting B squared minus 2B plus 25 equals 0. And if we just use the quadratic formula on this, did I do this right?
Minus 25.
I've actually moved everything to the right side. I tried to be fancy and do a couple things in my head there. I think I've got it right, but if I don't, somebody please tell me. So B is equal to 2 plus or minus the square root of 4 minus 100 all over 2, and this is certainly not in cubes. So we have a contradiction here in that case. In the other case, B is equal to D. All right, well, that bottom equation would tell me that B equals D equals 5, or B equals D equals -5, right? In order for their product to be 25 if they're equal to each other. So we can kind of plug those values into the second equation. If B and D are equal to, let me make a second little column here. If B and D are both equal to 5, then I have 10 plus AC is equal to 2, right? From this line right here. And remember that C is equal to -A. So this is 10 minus A squared equals 2. So A squared would be equal to 12. And again, that means A is not in cube. So that's a contradiction. I'm sorry?
Same contradiction, but
Oh, did I get yeah, that's right. Where's my eraser? 12 minus, or sorry, 10 minus 2. 8. Okay, probably I'm thinking to this one. So over here, if B and D are equal to -5, then we have -10 plus AC equals 2. So in that case, again, if I replace A with, with C with -A, I'm going to get something absurd here because, well, A squared equals -12. So again, A is not in Q. So every single case, I know I wrote that out fairly quickly, but it's kind of a routine set of steps in all of these cases. We prove that something that we required had to be rational is not going to be rational. So I think I've closed the loop on every possible scenario here by which we therefore prove that this factorization does not work. If you can't factor it as a product of quadratics, and if there's no roots, then it doesn't factor, right? This thing is the irreducible polynomial for radical 3i plus radical 2 over q. Okay. And so now, of course, we can, write down the degrees of everything here. The degree of I over R would have been 2. The degree of I over C would have been 1. And the degree of radical 3i plus radical 2 over q would be 4. So these are just the values that we would get based on the degrees of the polynomials that we've derived here. So pretty straightforward. Okay, questions, comments, complaints, ideas? Everybody got this written down yet? No, we're still working on it?
A little bit.
A little bit. Let me come back. Yes, question.
Got two questions.
Okay, let me take your questions and then I bet I can erase that.
All right.
Yeah.
So is the degree of basically anything over C gonna be 1?
Yes, the degree of anything over C will be 1, and the degree of any U that's already in the base field F will be 1. As kind of a more general observation. So maybe it just as well, I know you have another question, but let me just write that down first. The degree of U over F is equal to 1 if and only if U is an element of F.
Right.
Yeah, certainly we can say that.
And then my second one was just the irrational polynomial
Yes.
divides G of X. Is that in terms of polynomial division?
Yes, yes, right. So if I did g of x and I long divide it by the irreducible polynomial of u over f, I'll get a quotient, but the remainder will be 0.
And the quotient could be a polynomial.
Yes, very likely would be a polynomial. Yeah, unless g of x had the same degree as the irreducible polynomial. Yeah, that's right. Other questions, other comments? Any confusions here? Okay, if not, then what I want to do is, I said there's two very big theorems to do today. Both of which I want to very carefully write down. And we're gonna do the first one right here. Do the first one right now. And if I had done these half of the problems on that review sheet from the review session rely on one or both of these two theorems. So I was kind of constrained yesterday to be able to do some of these, but now we'll be able to do them. So the first one is theorem 11.7. And I'm going to call this the simple extension theorem. I don't think the book uses this name, but I like it. I'm going to have fancy names for both of the theorems today. So simple extension theorem. And let's state this theorem. So let's let F contained in K be fields. And I'm going to again grab an algebraic element, U. So let U be algebraic over F. Okay, so U is algebraic over F. And let's assume, since it's algebraic over F, it'll have a degree. Let's assume that the degree of U over F is some number n. So that just means that's the degree of the irreducible polynomial for F. Okay, so if we start off with that assumption, let's state these things in the right order here, sorry. Then there's three parts that I want to go through here. So then, three things. First of all, if we look at the simple extension f of u, I'm now going to try to start understanding the structure of this field a little bit. All we have for the definition is some vague statement about being the smallest field containing f and u. I'd like to describe it a little bit better. And what the better description is we take the polynomial ring f of x and we mod out by the principal ideal generated by the irreducible polynomial for u over f. Okay, let's just remember that this is a irreducible polynomial, which means that this is a maximal ideal that we have as a principal ideal, means that the quotient is a field. We already know this is a field, so this seems reasonable. This seems reasonable. So while I'm writing down the other two parts to the theorem, start thinking about how we're going to prove that. Start thinking about how we're going to prove. I'm going to ask somebody in a minute. Okay, the second step is, or the second result is that if we form this set, I'll call it S, consisting of 1 u squared and dot up to u raised to the power of n minus 1. This is a basis for the simple extension f of u over f. Okay, so remember that when we have one field containing another, we can view the larger field as a vector space with coefficients or scalars coming from the smaller field. So at this moment, when I'm addressing item 2 here, I'm not really thinking about f of u as a field anymore, right? Even though that is what it is. I'm viewing it now as a vector space where I'm not allowed to do regular multiplications anymore. I'm only allowed to do addition and scalar multiplication, right? When we work in a vector space, those are the operations that we have, addition and scalar multiplication. Well, turns out that if we want to write down the elements of f of u, right, where we only are allowed to do addition and scalar multiplication, they would all be expressible as uniquely as linear combinations of these lower powers of u, okay, up to the n minus first power. And then the third statement here is basically a trivial one, which is just stating then that if we look at this f of u colon f. Do you guys remember what this was, this notation? Well, in group theory, it was the index of a subgroup inside of a group, but last week in the sort of that quick overview handout that we went through, let's just recall. So first of all, the formula is going to be n. What is this? This just stands for the dimension over f of u. So it's just the dimension of the vector space. And so this is trivial. But item 3 is trivial because if you believe item 2, item 2 shows you how many things, I mean, what is the dimension of a vector space? It's how many elements are there in the basis. So I look at my basis in part 2, I've got n things there. So of course, this dimension is just n. So item 3 will require hardly anything more than a passing breath to sort of get that statement down. But let's come over here and work on the proof. Okay, so I want to prove this result. Guys, does everybody see that? I mean, you can think of how important this theorem is. It's describing f of u as a field first in step 1. Then in step 2, it's describing the same f of u, but as a vector space, right? Like if you want to describe a vector space, one of the best ways to do it is to give me a basis for it, right? So what we learn in linear algebra, like if you ask me what's the most important concept in the theory of vector spaces, I'm probably going to say basis, right? You got to have a spanning set that's linearly independent, right? We spend a ton of time on that in, pretty much every linear algebra class that I've ever been associated with. There's always a long conversation about basis. So yeah, so it's a really important theorem for describing this simple extension as something other than just this vague smallest field that contains f and u, right? That's kind of vague. It's like, yeah, I got this abstract idea what the field is, but now we can describe the isomorphism type of the field, and we can describe the vector space structure of the simple extension as well. So it's like a win-win kind of theorem here. So let's talk a little bit about the proof, and we'll kind of go in order here. I've already pointed out that item 3 is kind of just a afterthought, a trivial little afterthought. Let's start with item number 1. How are you going to prove it? I've been stalling to give you a chance to think, how would I prove this isomorphism?
First isomorphism theorem.
You got it. We've got a quotient ring, right? Isomorphic to something else. It's going a little bit backwards because normally we have the quotient on the left side, but we're going to start with f of x, map it over to f of u. Hopefully the kernel will be this guy, and hopefully it'll be onto. Let's see if we can do it. Okay, so let's do that. Let's define, we use the first isomorphism theorem. Right, that's how we're going to do it. We're going to use the first isomorphism theorem. So I'm going to define, I'm going to use the same notation that the book is using in their proof. So I'll use phi for my isomorphism. And phi needs to go from f of x, the polynomial ring, over to the simple extension f of u. And I need to define that via phi of, so I'm going to take some polynomial f of x, and I have to spit out something that's over here in the field f of u. Does anybody have an idea how I could plug a polynomial into phi and find a way to spit out something that's in f of u? This is like a key step. We got to get the function defined correctly if we want to have any hope for things to work out the way they're supposed to.
Would it be like a plus b with u?
So in other words, you're thinking about it if we wrote out the coefficients of the polynomial in detail. Yeah, I mean, if we were, maybe I'll scribble over here for a second. If we had phi of, a plus bx plus cx squared or whatever, right? Then what you're saying, Larry, is that I would output what?
I would have like coefficients with u as the mystery x.
In other words, putting in, basically evaluating, right? Evaluating the polynomial at u. because this kind of an expression lives in f of u, right? F of u is closed under everything you see there. So I would absolutely do that. And so this would just be f of u. We would just evaluate the polynomial at u, okay? Now this needs to be a homomorphism, and we're gonna have to check the kernel and make sure that it's surjective and all that good stuff, right? So phi, I'm gonna do this part pretty quickly, guys, because the homomorphism part is quite straightforward, right? For the homomorphism, you know, if you take phi of f of x plus g of x, right? The way the formula phi works is you just replace x with u. So you just get f of u plus g of u, but that's just phi of f of x plus phi of g of x. So I really don't have a whole lot to get nervous about with that. And of course, the multiplication is equally easy. If I have phi of f of x times g of x, again, this is a ring homomorphism. That's why I'm checking both the that phi respects both addition and multiplication, the operations in the ring. So this just becomes f of u times g of u, and that's just phi of f of x times phi of g of x. So absolutely no surprises on that part. Okay, then let's check the kernel part. The kernel of phi, we would love it. We would love the kernel of phi to be this irreducible polynomial here, right? So let's take a look at that. Is everybody okay so far? I don't want to go too fast. I'm not trying to slough anything under the rug here. But the way, whenever you use an evaluation map to define a function, right? It almost always pretty trivial to show that it respects the addition and multiplication. So that's all we're doing here. We're evaluating f of x at x equals u. Okay, let's check the kernel. So f is in the kernel of phi. I'm going to try and do this as an if and only if kind of a chain, right? So I would have a function in the kernel of phi, if and only if when I take phi of f of x, I should get 0. That's the definition of kernel. But of course, phi of f of x is just f of u. Okay, so f has to be a polynomial that has u as a root. Aha, well, that tells me that that is equivalent to saying that, remember, guys, that was the third remark in the recap. Can you still see it there? Not really. It's in the notes at the beginning. It said that if g of u was equal to 0, then the irreducible polynomial divides g of x. So this just tells me that IRR of u comma f divides f of x in this case. And that's just another way of saying that f of x, I'll just call it f here, lives in the principal ideal generated by the irreducible polynomial over f. So there you go. The kernel of phi is exactly what you're hoping it would be, which is this principal ideal. So let's summarize that here. The kernel of phi is this principal ideal. Excellent. Okay, so we've got the homomorphism. We've got the kernel being what we want it to be. I just need to make sure that this is surjective. Actually, if I want, I don't really need it to be surjective if I just want to use Annen's version of the first isomorphism theorem. Let's just do that. Let's use Annen's version. Got to get myself in the notes here. After all, I'm sure you guys, when you get your houses someday, choosing your wallpaper, you'll probably take these notes and put them up on your walls. So let's make sure that we memorialize this very carefully. Annen's version of the first isomorphism theorem. So what does my version of the theorem say? Well, it says if you take f of x and mod out by the kernel, which is the principal ideal generated by the irreducible polynomial of u over f, My version of the theorem says that it's isomorphic to whatever the image of phi is. So in other words, it's just phi of f of x. Okay, so whatever that happens to be. Of course, we will need it to be f of u. Okay, clearly, whatever the image of phi is, it lives inside of f of u, correct? I mean, f of u is my receiving space for this homomorphism phi. So, I certainly know this, right? Everything lives inside of f of u right now. Okay, so the image of the homomorphism is certainly going to be in there. I'm going to try to convince you that the containment the other way, I'm going to try to convince you that this containment works the other way, which would then mean these are equal, which would then give me the final thing I need for this first point. Okay, almost done. We're almost done here. With me? Now, would you guys agree? Let's just note here that these markers are very good today that I brought up here. Would you agree that the image of capital F of X already contains U itself? I think so, because I can apply phi to any polynomial I want. What if I apply it to the polynomial f of x equals x? Phi of just x would be u. So u is in this image, right? So I'll just say here, since u is equal to phi of x, if we apply the homomorphism to x, all we're doing is evaluating x with, we're taking x and we're plugging in u everywhere we see an x, right? So phi of u, phi of x would just be equal to u. And is everybody okay with that? Yeah. Is that good? U belongs in. So, I mean, we're looking at just the outputs of this function. So we're taking phi of every possible polynomial under the sun. And we're just saying, what are all the things that come out of that? Well, one of the polynomials that I'm allowed to plug in, because it is a polynomial, is just x itself, right? X is a polynomial. I'm allowed to take phi of that. How do I take phi of that? Oh, I just replace everywhere I see an x, I change it to a u. So phi of x is equal to u. So u is one of the guys that's in this image, right? But there's also something else that phi of f of x contains. It already contains, it actually already contains all of capital F as well. And that's because if I take any A that belongs in the base field, that is phi of the constant polynomial A. So included as inputs to phi would be constants, right? Constants are part of f of x. And if I take phi of a constant, I don't really have to evaluate u because u is getting plugged in for x. Well, there's no x here. So I'm literally just outputting the same A again. Okay, is everybody with me? It's a beautiful argument. Really is. Guys, this is a field. This is a field already because I'm modding out by an irreducible polynomial. That means this is a field, which means this is a field. But it's a field that contains U and capital F. But I thought that the definition of f of u was that f of u was supposed to be the smallest field that contains u and all of capital F. I have now come up with another field, right, that contains u and contains capital F. So it has to be bigger than the other one, because this is supposed to be the smallest one, right? So let's just write that down. Since phi of f of x is a field by the isomorphism above, just so it's clear. the isomorphism above that we already have established using Annen's version of the first isomorphism theorem, right? That already establishes that this is a field containing capital F and containing little u. Then remember that it's not possible for this to be a proper subset, because then this thing wouldn't be inside of here, right? F of u, so then F of u, which is the smallest, you can't have anything small, you can't have anything strictly smaller than this that contains F and u. So this is something that contains F and u, it better not be strictly smaller, right? So then F of u is actually, it has to be, well, let's just say, I'm just gonna go straight to equality here. It equals phi of F of X by definition of F of u. Does everybody understand that? F of u is the smallest field that contains capital F and u. We have come up with another field that contains capital F and u, which on the surface of it looks smaller. Oh, but it can't be smaller, right? So therefore, these have to be equal. Yeah. Great, so as soon as this is an equal sign, number one is proved, right? Number one is proved. Clear enough? Clear as mud? Hopefully not, hopefully better than that. Guys, this is an important theorem, so I do want you to understand this proof. It's a pretty simple function that's being defined, but I just love the use of the first isomorphism theorem. And, you know, we're using results that we proved in these last couple classes, as well as just the definition of F of u to do the problem. It's there's some proofs that you don't learn a lot from. It's just as tedious calculations, you don't feel like there's a lot to gain from it. This is not that kind of proof. This one actually has substance to it. Is actually using the tools we've been learning this semester, and so I really like to present it. Okay, let's look at number two. Item number two. So item number one is a great description of F of u as a field, right? It's one of these quotient fields, or quotient rings. Now we're going to look at how to think about F of u as a vector space. Okay, so as a vector space, let's, what's it say over there? S is a basis for F of u over F. Well, to be a basis, I have to be linearly independent and I have to be a spanning set. So let's talk about that. S is linearly independent. I got to verify that. Do we remember how linear independence works from linear algebra? Oh, my 250B students hate this definition. Linear independence is the one where you start off with a linear combination of the vectors that cancels out to zero, and then you try to prove that all of the scalars are zero, right? Okay, this is something we see in like 3 or 4 or 5 different math major courses, so it's kind of a big deal. So I'm going to assume here, see what do I want to use for my scalars. So I'll use C. So C0 times 1 plus C1 times U plus C2 times U squared and dot, dot, dot up to C sub n minus 1 times U to the n minus 1. Let's assume that that is equal to 0 for some scalars C sub I. Those scalars are in the scalar field, which is capital F right now. Okay. So thus, in other words, let's just go ahead and write it out. C0 plus C1U plus C2U squared and so on, plus Cn minus 1 U to the n minus 1 is equal to 0. And that just means that U, if we look at just the bare bones of what that says, U is a root of a polynomial right now, right? So thus, U is a root of, I'll write it as f of x, which is just the polynomial c naught plus c1x plus c2x squared and dot, dot, dot plus cn minus 1 times x to the n minus 1. But I see a real problem right here. I see a real problem here. Does anybody see the problem with this, or the issue that we're going to have with this? Larry?
If U is the root of that, then it has to be a multiple of our irreducible.
Exactly. This f of x would have to be a multiple of our irreducible polynomial, right? That was by that third remark today. If u is a root of any polynomial, then that polynomial must be a multiple of this minimal polynomial that we talked about. So this means, so hence, right? Hence, what we're saying is that the irreducible polynomial for u over f has to divide f of x. In other words, f of x has to be a multiple of it. Well, that's not looking too good. That's not looking too good because the irreducible polynomial for u over f has degree n. And now here we're saying that f of x, which supposedly has lower degree somehow, right, is a multiple of this. So this has degree n, this has degree n minus 1, supposedly. The way it looks like it has degree n minus 1. We're about to shoot that idea down. But it looks like this has degree n and this has degree n minus 1. How could something of, that's a multiple of something of degree n have, lower degree like that? Like, what's the only way out? Like, that we don't get some kind of a contradiction to the definition of this polynomial?
Coefficients have to be true.
Yeah, f of x itself has to be 0, right? The only multiple of my minimal polynomial that would be allowed to have a lower degree than that minimal polynomial would literally be 0, right? Because you can take this polynomial and multiply it by 0. So I'm just going to say here, guys, by degree considerations, f of x has to be 0. That's the only possible conclusion. If f of x was not 0, then we would be saying right now that this f of x was somehow a better witness than the minimal polynomial was for u being algebraic over f. Great. So if f of x is 0, if f of x is 0, well, and this does not mean the number 0, right? This means f of x is the 0 polynomial. So it would be this polynomial, right? If we want to think of it that way, it's a polynomial. And now you see all the c's are 0. Okay, so C0 equals, this is what you wanted to prove, right? This is how linear independence is proved. Anybody knows how to teach this to my sophomore students, you're more than welcome to hang around after class and I'll let you try. It's not the easiest thing in the world. It's a really tough concept. First time you ever see linear independence. I think it's a tough concept for the students to understand. But that's the definition. Okay, so S is linearly independent. The other part of being a basis is it has to be a spanning set. So that's going to be the next thing here. S spans f of u. So what that means is that anything in f of u should be expressible as a linear combination of the elements of S. So we're going to start with some random thing in f of u. Let's see, what do I want to call it here? Take some random polynomial. Oh, I'll just use little f of x again. So little f of x, let little f of u be in capital F of u. So it's just, actually, hold on. Is that what I want to do? Sorry. I want to use this isomorphism to write any element of f of u essentially in some equivalent way using a polynomial. So let's do this. Let's let little f of x be an element of capital F of x, be arbitrary, and consider essentially consider the corresponding element f of u under that isomorphism that we had written down earlier. Now, so that would be an element of capital F of u. So we take an arbitrary polynomial And then we evaluate it at U, the same way we did in the first part of the proof. Now, what I need to do actually is apply the division algorithm here to this polynomial. So what I'm going to do is I'm going to use the division algorithm. To write f of x as, so what am I going to do? I'm going to actually divide f of x by the irreducible polynomial. So I'm going to take it, and there will be a quotient q of x times the irreducible polynomial of u over f plus some remainder, which I'll call r of x, where the degree of the remainder, this is how the polynomial version of the division algorithm works, the degree of the remainder has to be lower than what you divided by. The irreducible polynomial had degree n by assumption, so this is at most n minus 1. This is at most n minus 1. Okay, so now what I do is I evaluate, what I can do is I can evaluate both sides at u. Right, I can evaluate both sides at u. So evaluate at x equals u. And what I'll get is f of u equals q of u times, well, when I evaluate the irreducible polynomial at u, what do I get?
0.
0, right? You're plugging u into its witness polynomial. That would be a 0. Plus r of u. Okay, so it turns out that this element f of u that you wrote down is actually not so mysterious after all. It has to actually be equivalent or actually equal to r of u, and r of u is a polynomial of degree less than or equal to n minus 1. So we can actually write r of x as, I don't know, let's say a naught plus a1 x plus dot 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 plus a n minus 1 times x to the n minus 1, where all of those a's come from the base field, capital F. And so then f of u would be equal to r of u, which would be equal to a naught plus a1 times u plus dot 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 plus a sub n minus 1 times u to the n minus 1. And look at that. Look at that. We have written this arbitrary element of f of u as a linear combination of exactly what we're claiming the basis to be, right? So this expression here, this expression belongs to the span of 1 u squared and dot 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 up to u to the n minus 1, which is what S is. Right. So anything in f of u can be expressed in terms of, actually that is not equal to S, I'm so sorry. It's just the span of that, sorry, not equal to S. I mean, I guess we could say that this is in the span of S. That would be a more correct way to write it. It would belong to the span of S. So anything in f of u is in fact a linear combination of the elements of S. Yeah. Great, so that is a linearly independent set that spans f of u. So we have a basis for f of u over f. And then I've been waiting to do this all afternoon. From there, we just point out that the third statement is just totally clear at that point. Okay, it makes sense. What do you think? Let's do a quick example of this. Just play with an example. Took a little while, didn't it? Oh my gosh, it did take a while. That's okay. So let's take the base field to be the rational numbers. And let's take u to be the 7th root of 2. Now what I'm going to do is I'm going to I'm going to ask you, first of all, what is the irreducible polynomial for U over Q? In other words, can somebody give me a polynomial that is satisfied by the seventh root of two?
X to the 7 minus 2.
Great, x to the seventh minus two, and is that irreducible over Q? Or should it be factored down lower? Irreducible over Q by,
Oh, that's great.
yeah, Eisenstein's criterion, right? So we can use Eisenstein with what value of P? Two, exactly. So this is the irreducible polynomial for U over Q. And what I'd like to do is I'd like to write a basis. So a basis for, can you guys all see over there? It's okay?
Yeah.
All right, great. So a basis for Q of the seventh root of two over Q is, so if we just, this is a simple extension, right? I'm setting myself up exactly to use this. We have n equal to 7 here. So all I've got to do is start writing down the first 6 powers of the seventh root of 2. So that would be 1 and the seventh root of 2 and the square of that, which would be the seventh root of 4, and then the seventh root of 8, and then the seventh root of 16, and then the seventh root of 32. Why did I have to pick such a big number? 1, 2, 3, 4, 5, 6. And then the seventh root of 64. Right? Everybody with me? You see what would happen if I kept going? The next one in the list would have been the seventh root of 128. But the seventh root of 128 is just 2. Right, 2 to the seventh is 128. So if we kept going, the next thing we would list in this natural progression, if somebody walks in the room right now and you ask them, what's the next thing in the list? They're going to say seventh root of 128, but that's equal to 2, and that would be linearly dependent on the first vector in the set, right? I could make a linear combination, namely 1 times 2 minus the seventh root of 128 would cancel out to 0. That would be linearly dependent. But these guys are linearly independent. Okay, so I don't know if that would have been obvious before today. Like if you take a linear combination of all these terms and set them equal to 0, the only way that that can work is if all the scalars are 0. This is kind of neat. Okay. So that's the vector space viewpoint on this example. Also, we could also maybe up here, I have enough room to do it. We could also recognize that Q of the seventh root of 2 as a field using the first part of the theorem, it would be isomorphic to Q of X modded out by the principal ideal generated by X to the seventh minus 2. You see, guys, basically what you're doing here, my friends, is you are basically identifying X to the seventh with 2. Okay, you're basically setting X to the seventh equal to 2 and then putting it up there where X is, which is what you have on the other side. So it's a totally, expected isomorphism, I think. I would definitely expect that isomorphism. Okay, how are we feeling? Time for a break?
Yeah.
I think so too. So this is the first of the 2 theorems. When we're done from our break in about 10 minutes, we will talk about the other big theorem from today's class, which is the Tower theorem. So yeah, let's take a break till 5:15. I totally agree with that. Yes, sir. I am going to, speaking of the 2-hour time, I want to make sure I get done with this on time today as well. We proved the simple extension theorem. I have another theorem for you now that's equally important, and there's tons of applications of it, and I'm torn between whether I should do the proof first or the applications first. I think I'll probably do the proof first, just since I'm in proof mode today, and we only have to wait 2 days for the application. Wednesday, we're all coming back, right? hopefully. Okay, so let's state this theorem 11.4. It's called the Tower theorem. What this, I call it the Tower theorem. I don't think Hungerford refers to it that way, but it's a fairly standard way to call it. And what it is you might have this following situation. Let F be a subset of K, be a subset of L. Okay, be a chain of fields. So this is a chain of maybe several fields such that the dimension of K over F is finite and the dimension of L over K is also finite. So I'm using this same index notation to denote that. So then here's the conclusion. The dimension of L as a vector space over F is also finite. And the important equation is this one. The dimension of L over F can be obtained by taking the dimension of L over K times the dimension of K over F. This is the Tower theorem. Okay. So let's see if we can do the proof of this first, and then we'll get to the examples. The examples are really powerful. You're going to be impressed with this theorem, what it allows us to do. But before we can do that, I do think we should do the proof of this. So this is an easy one to kind of remember. Hopefully, you just have, it's the same kind of theorem we would have had for subgroups in group theory as well. So here's the proof. Essentially what I'm going to do is I'm going to start with bases for K over F and for L over K. And then I'm going to somehow create a basis for L over F. Okay, so let's set this up. Let's get some actual notation here. Let's assume that the dimension of K over F is M. And that the dimension of L over K is N. And so then let's actually write out some notation for the bases that we're going to use here. So let's let this, by the way, this whole proof is totally linear algebra, right? It's just the 307 kind of proof. So then what I'm going to do is I'm going to write down a basis here. Let's call the basis for, let's call the basis for K over F a U1, U2, and dot, dot, dot up to UM. Let's let that be a basis for K over F. And then let's let the set V1, V2, and dot, dot, dot up to Vn. Be sure to get your M's and N's straight. This is going to be a basis for L over K. Holly, you don't look too happy. Are you okay?
Is it supposed to be M-1 and N-1, or is it supposed to be? M?
No, these are just M and N. Yeah, these are just M. So this is just, I don't even know what these numbers are, but I'm just assuming this dimension is M. So
Oh,
my
I see.
basis should have M vectors in it,
Okay.
right? And this one is N, so the basis should have N vectors in it.
Okay.
Right. Okay, great. Well, the claim, can I write the claim down here, guys? Can you see it? No. Let's put it here. I'm trying to save space. Good for the environment. So here's the claim, is that I can actually get a basis, and this is something that is quite neat to write down. The claim is that if we take any of the U's and multiply them by any of the B's. So if I take a U question.
It's just kind of stressing me out there. Laptop is like half that's
You know, it'd be a terrible thing if this thing fell to its death. You know that.
You like that puzzle?
It's basically, if you like that puzzle, that's right, it would happen twice in the same day, and that would be really a bad coincidence. I'm not sure which one's worth more money, actually. This thing is a piece of junk, trust me. I'm just waiting for an excuse to tell the university to give me a new one. So if it falls off the table, I can just blame one of you guys, and then I'll go over there and say, my student knocked this off the table, give me a new laptop.
Isn't it reporting right now?
It is.
We should all collectively knock.
I will learn how to edit this video.
Ah.
You guys are gonna get me in trouble. Okay, so let's see here. What am I doing? I'm trying to create this, this basis, I'll call it S. I'm gonna claim that that set right there is a basis, right? Is a basis for L over F. So I've got to do the usual two things, just like we did earlier today. I have to check that this is linearly independent. I have to check that S is linearly independent, and I also have to check that S spans L. Right? So let's check it out. So check S is Li. Start with the linear independence again on this one. And now how does that work? We start with a linear combination of, and by the way, this is a multiplication here, which is happening in L, right? This is happening way up in L. Even if the U's only live in K, but of course, K is also inside of L. So it's all really happening within L. So this makes sense to take a UI and multiply. Normally in vector spaces, we don't multiply things together, but we can do that if we're working in a field. And L is some big universe field that we can imagine everything is inside of. So I'm allowed to do this multiplication here. Let's check it. I'm going to assume that I have a linear combination of these UIVJ products. And we are actually going to use a summation notation to denote all of this. So I'm going to do a summation where I ranges from 1 to M and J ranges from 1 to N of AIJ times UI times VJ. And I'm going to assume that that is equal to 0, where the A sub IJs live in the base field F. That's because we're proving that S is a basis for L over F. Over F. So the scalars are coming here from F. So the AIJs are coming from F. So this is just some big linear combination. There are actually MN terms in that summation. And what I'm going to do is I'm just going to put some parentheses in here for a minute. So I'm going to break this down, and this is kind of like almost could be represented as a double sum. So I'm going to imagine this with, I'm going to put the J on the outside, summation J going from 1 to N of a summation I going from 1 to M of A sub IJ times U sub I times V sub J. And of course, this is all still equal to 0. I have not done anything here. The expression on the left is literally well, it looks like it's now two sums. It's really just breaking apart one large sum that we had in the first place. Now, what do we have now? This is a linear combination of just the VJs. I want you to imagine that. And where do the scalars live? Well, those U's live in K, right? So what do I have? I have elements of L. That's what the V's are, right? I have elements of L with coefficients from K. And I'm adding all that up and it's canceling out. But remember, guys, that these V's are already linearly independent. They are already a basis for L over K. So if I have a linear combination of the V's with coefficients in K, right? These coefficients are in K, then because the V's form a basis, they are already linearly independent. So let's just say it that way, right? Since V1, comma, V2, comma, dot, 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 comma, Vn is a basis for L over K. This set is Li. If it's basis, then it's Li. And that means that anytime I have a linear combination of those vectors canceling out to 0, the coefficients have to be 0, right? So what this means is therefore, right, thus, for all J, if I perform the summation I going from 1 to m of aij ui, I have to get 0. Each of those coefficients is 0 for each fixed j. For each fixed value of j, that would be 0. But now what do I have? I have a linear combination of the u's. The u's live in k, right? They are a basis for k. I have a linear combination of the u's with coefficients from the base field f, right? And since the u's are a basis for k over f, they have to be linearly independent, meaning that the coefficients are 0. I just said a lot, I need to write it down, right? Okay, so since the set U1 ... up to UM is a basis for K over F, this set is also Li. And so if I take a linear combination of a bunch of vectors that are Li and it cancels out to 0, then the scalars are 0. So thus a sub ij is equal to 0. This would be for all I and j. So that's how you prove linear independence, right? You prove that the coefficients, right, in that linear combination all cancel out. Or that they're all equal to 0, I should say. They're not necessarily canceling out, but they are just all equal to 0. Pure linear algebra. If you didn't know better, you might think you're in a linear algebra class right now. All it is. Let's check the spanning part. To be a basis, I have to be linearly independent, but I also have to span my vector space. Okay, so let's check that over here. I'm going to check over here. I'm going to check that S spans L. Check that S spans L. Let me just say over F. So, in other words, everything in L should be expressible as a linear combination of the vectors in S, but using scalars from F to do it. Okay. Well, that means if I want to check that S spans L, right, that means I'm going to pick an element out of L and try to write it as a linear combination of the set that I'm hoping is my spanning set. So let's see if we can do it. I'm going to call this vector W. Let's let W belong to L. Hopefully, I can write W as a linear combination of the guys that are in S over there. Now, the thing is, I already have a basis for L. I already know that everything in L can be written as a linear combination of these V's. So let's start by doing that. Let's start by doing that. So I'm going to use the fact that since the set V1, V2, and ... up to Vn spans L over K, right? Then W can be written, I'm going to write it as B1, V1 plus B2, V2. I guess I'm going away from the summation notation for a moment anyway. Oh, did you guys notice that I actually put, this is because I'm so trained in my 250V ways, I put arrows on some of my vectors here. It's not wrong to do that because they are vectors after all, but technically in this class, I generally don't have to do that because you guys know what I'm talking about. At least I think you do. So I don't really need to be writing down the arrows on top of the vectors here, right? So we can write W in that form. Now the scalars, the B sub i's here, they are going to be yeah, they are going to be scalars in K, right? Because the V's are spanning L over K. Right, so that's fine. We write W that way. But because the B's live in K, guess what? They can be expressed as a linear combination of the U's because the U's are a basis for K over F. So for each of those B sub i's, I'm gonna do that, right? So for each I, we can write, well, let's say it this way, for each I, since the set U1, comma, U2, comma, dot, 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 up to UM spans K over F, since we know that, right? B sub I can be written as, well, it would be AI1 U1 plus AI2 U2 plus dot, 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 plus AIM UM. And this is where the AIJs are in the field capital F. I can write it like that. For each of those B's, I can get away with that. Only thing here is you just gotta keep all your I's dotted and your J's dotted and everything in the right order. Make sure you don't lose track of anything. There's really nothing bizarre that shows up here. And it's also really, to be honest with you, it's not a massive amount of creativity. This is mostly just following the definitions. What does spanning mean? What's a linear combination? The definitions, classical definitions from linear algebra. So at this point, I'm going to go back to W again, and I'm going to rewrite it, not with just the B's and V's, but I'm now going to insert what the B's are here, right? So then let's see what we get. If we now look at what W is, I can take B1 and write it as A11 U1 plus A12 U2 plus dot, 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 plus A1M UM times V1 plus, and then I will clean this up in a minute. I'm just trying to show how it kind of falls out. The B2 would be A21 U1 plus A22 U2 and dot, 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 up to A2M UM times V2. And this goes on and on and on. I'll just write dot, dot, dot here. But the main point is that we can eventually rewrite it now as a summation. Right, if you think about it, every single one of these terms has, well, it has an AIJ times, it looks like the U actually is going with the J coefficient here. So UJ and VI, is that right? The first subscript is indexing the V and the second subscript, that's a little bit annoying. But it doesn't really matter. It just means that I've kind of, well, let me just interchange. So let me rewrite this again as UI and VJ, because I want it to look like the set S over there. So I can do that. I just have to be willing to put AJI here. Sorry about this, guys. I'm just switching the roles of the I and the J for a moment. And so the I goes from 1 to M like before, and the J goes from 1 to N like before. So that's exactly what I wanted. Nikolai?
Do you need to change anything with the W times all the B's that you were saying?
Nothing up here will need to be changed. It's just this last part down here. If I want to get UI and VJ, it's actually going to end up being, yeah, the AJVI term is what the coefficient is going to be. But this thing here is in the span of S. It's a linear combination, and it's a span over F of a bunch of vectors that are in S. So that kind of takes care of it. Okay. Yeah. That makes some sense to everybody?
The second part of the proof for spanning could be done with uniqueness the whole way through, right? You just take the scalars to be unique because you have a basis, and then you don't have to worry about the LI.
Yeah, I know you like the other definition of a basis where it's every element can be uniquely expressed. Yeah, you certainly would be able to do the proof using that alternative definition. I haven't actually taken the time to do it that way myself before, but it would be doable. Yeah, definitely. I like to break it up into the two parts, but that's just me. Is everybody okay with this proof? both of these big proofs we've done today, I will probably be asking you to learn them again. Like officially learn them again, maybe not for next Wednesday, but at some point there might be an opportunity to show me that you know these proofs. So it's definitely worth, I know you've all written them down, but definitely reflect on them a little bit when you have a little more time. Yeah, make good sense of it. But I would like to show you some applications of this tower theorem now, and I'm not gonna have time to do more than probably one of them today, but on Wednesday we'll do several more. And this is the kind of, these applications are the kind of questions that I will definitely be making an effort to include on my midterm next week and also in some of the review session problems. So let's do some applications. And so this is just number one. We're probably only going to get to number one today. But this will already give you, you're already, I think, going to appreciate the theorem. So here is a good example. Compute the dimension of Q of the sixth root of 2 as a vector space over Q of the square root of 2. Now, whenever you have this notation, you're always viewing, this is like your K and your F, right? So you have to be thinking of this thing as containing this thing. So does everybody agree that this field contains this field? You would need to convince yourself that square root of 2 lived in here. But it does, because the square root of 2, just as a side note here, before we actually do the problem, note that the square root of 2 is in the larger field, because if I take the sixth root of 2 and cube it, right, it's in that larger field.
Well, either.
Oh, equals, yeah. Yeah, exactly. So thus, Q adjoin square root of 2 is inside of Q adjoin the sixth root of 2, right? As soon as, you know, you've got, as soon as you've got radical 2 in here and Q is already in here, then all of this is inside of there as well, because this is, after all, this is a field. So it's going to be closed under all of the field operations. I guess what I'm trying to say, guys, is make sure your notations make sense. I should not see something like this. Right? This doesn't make any sense, because Q of radical 3 is not a subfield of Q of radical 2. This is always, whenever I'm using this notation, it should always be with a base field inside of an extension field. So the thing on the left should always contain the thing on the right. This is just to make sure it's even making sense, right? So when I write something like this down, I just want everybody to make sure that it makes sense. Does this field contain this field? Well, it sure does, because everything in this field is over here. Specifically square root of 2, which is the only thing you might be nervous about. It does exist in the larger field, as this little calculation shows. Okay, but now the question is, what is the dimension of the vector space Q of sixth root of 2 over Q of the square root of 2? You know, I know that there's a polynomial here that radical 2 satisfies, right? So radical 2, you don't need to write this down yet. I'm just scribbling for a moment. The square root of 2 satisfies sixth root of 2 satisfies this polynomial, right? And so over Q, this is irreducible. And so over Q, the dimension of Q of the sixth root of 2 over Q is going to be 6 by the simple extension theorem today, right? Remember that? The dimension of, right, what was it? The dimension of F of U over F. This is from the first theorem we did earlier today. It was just n, right? The dimension of the irreducible polynomial. So if I wanted the degree of Q of sixth root of 2 over Q, the answer would be 6, because the irreducible polynomial for the sixth root of 2 is this one. This is irreducible over Q by Eisenstein applied to P equals 2. Wouldn't that be nice? Okay, but the problem is I have to get nervous now that if I allow a larger base field, not just Q, But Q of radical 2, I have to be nervous now that, well, if I'm allowed more scalars, if I'm allowed to use more than just rational numbers in my polynomials, maybe I could find a cheaper polynomial than this one. I have a much larger base field here than just Q. So maybe there would be a better polynomial that would work, but gosh, irreducibility over this field, we don't have anything for that, right? So trying to figure out this dimension directly is hard, right? So let me just make a note here for the solution. Computing this directly is potentially hard. But what we can do is we can build a tower. When I draw the tower theorem, what I like to do is draw the fields vertically up and down. So I would put Q at the bottom. And then I would put the middle field, which is Q of radical 2. And then I would put the large field, which is Q of 6th root of 2. And we already know that this dimension was 6, right? So let me come over here and write some calculations down. Right, so let's just note here that the simple extension, I'm just gonna note that the dimension of Q of the 6th root of 2 over Q is 6. Since the irreducible polynomial for the 6th root of 2 over Q is the polynomial x to the 6th minus 2, and that is irreducible over Q by Eisenstein. Okay, so that's a 6. But then the dimension of, what do you think the dimension of Q of radical 2 over Q would be? What's that number going to be? It's 2, right? In other words, this number right here is a 2, right? Since the irreducible polynomial of square root of 2 over Q would just be x squared minus 2, also irreducible by Eisenstein applied to p equals 2, or you can just point out that there are no rational roots to this polynomial. Okay, so guys, if this is a 2 and this big thing is a 6, then what does the intermediate extension right here have to be according to the Tower theorem? 3, right? 3. This number times this number equals this number. That's how it works, right? So by the Tower theorem, the dimension of Q of the 6th root of 2 as a vector space over Q adjoin the square root of 2 is 6 over 2, which is, in other words, is 3. Now, you might be wondering, could I have still gotten that answer? Because, so the question is, could we have figured that out by writing down a cubic polynomial, for example? Right, so you might note that the 6th root of 2, this is the last thing we're going to do today, guys. 6th root of 2 does satisfy the polynomial f of x equals x to the x cubed minus the square root of 2. So if I cube this element, I get square root of 2. So if I subtract square root of 2, this would be 0, right? And this is a polynomial in Q of radical 2 of x, right? That's a perfectly good thing to consider. So, this third power suggests that, I'm not surprised that the answer here is 3, but there is a little bit of an issue with this, which is that to call this the irreducible polynomial for the 6th root of 2 over Q of radical 2 square root of 2, I would need to know that this is irreducible over this field. Right? So you're not going to use your rational roots test. You don't have Eisenstein's criterion. You don't really have a great idea how to approach it at all, right? It's a cubic equation. I don't really know how to think about the roots of that. So it's definitely not as easy to directly convince myself that this is the irreducible polynomial, but actually, we now know that it is. As a consequence, the fact that the Tower theorem tells me that this dimension is 3 actually then proves that this must be irreducible. If this factored over Q of radical 2, then this number would be smaller than 3. Right? So it actually cannot factor. It actually cannot factor. So as a side note, right, we deduce from this work that we've already done, we deduce that x cubed minus radical 2 is irreducible over the field Q adjoin radical 2. So irreducibility over a weird field now is what we have to establish here. Okay. What do you think? Make a little bit of sense? Guys, on Wednesday, we're gonna do a lot more. We're gonna do Tower theorem like this. We're gonna go this way. We'll put like cube root of 2 here, then we're gonna go this way, and we're gonna put like square root of 2 here. And we're gonna say, ooh, this is 3, this is 2. So now I'm gonna go up here. This is starting to look like a lattice of subgroups. We're gonna get something up here that has to be a multiple. So whatever I put at the top of this, I'm just so excited. Do I have to wait 2 days? Whatever goes up here, right, whatever this is, its dimension over L has to be at least 6. Because it's a multiple of 3 and it's a multiple. If I go the tower this way, it's a multiple of 3. If I go the tower this way, it's a multiple of 2. At a minimum, it's got to be a 6, right? And so if I can prove that it's at most 6, then I would be proving that it equals 6. We'll do that next time. I'm so sorry. I just get too wrapped up in my thrill of the adventure. It's like that moment